Good. Now I want to show you a different application for shortest path, namely where shortest path are really estimated, are used to estimate a discrete state. In particular, a state in an undirected probabilistic graphical model where the nodes are a chain, where they are a straight line segment. All right, and that maybe sounded more complicated than it really is. So I will motivate it using this example here. So a standard problem in computer vision is to try and get a depth map from two stereo images. Us humans, we're using stereo. And how do we do it? If I take an object which is nearby and you look at it with one eye or the other, you see that it jumps a lot. If it's far away, one eye or the other, it just jumps a little bit. So in other words, the disparity, so how far the shifted the object appears in one image relative to the other, that is a function of distance and is one amongst many cues that us humans use for distance estimation. We use many others, for example, so you know that our eye can accommodate or focus on objects which are close or far, and for that we use muscles, and we get some feedback to our brain, or so we feel if our eye focuses to some place close or far. This is one of the cues. Really important cue is also usually we're not standing perfectly still, but we're moving a little bit, or we're walking. And so, for example, this tiny sideways movement of my head that makes nearby objects shift a lot more than faraway objects. And all of this is amalgamated in us with a lot of prior knowledge and expectations and so on into a depth estimate, which is of course really important for not bumping into things, etc. Good. Now, for the computer, we have the same problem. Before the depth estimate, images are calibrated, and calibration means that, for example, if one camera is a little bit shifted with respect to the other, or rotated with respect to the other, I correct for all of that. And after, actually, I should write rectified here, not calibrated. I think that's the correct technical term, rectification. After rectification, I can, I know that if I take an image patch in one image and I want to know where to find it in the other image, then I only need to scan along this epipolar line. I only need to, I don't need, I know after rectification that I don't need to look in arbitrary places, but I only need to look left or right of the original patch. Now, as I was saying, for objects that are close by, the shifts are much bigger than for objects that are far away. So what we can do is we can take on this blue line, let me use a brighter color, we can use this patch, and now in the other image I can start from the same position and then I will look for how many, or I can evaluate the match the patch in the left image and the patch on the right image. And then I can do that for many different shifts. And I can always ask for each shift, how good is the match? And hopefully, if we have a good comparison function, also something that can be learned using a neural network, but if we have a good comparison function, and hopefully I will find the right match, and then I can ask, all right, how many pixels was this correct match shifted relative to the other image? And from the relative shift, I can compute the depth. Close by objects are shifted further than far away objects. So what we get is an image like this, where for each, I'm trying to figure out where we could perhaps be in that image. Maybe, I'm really not sure, but maybe we are somewhere here. So I can ask, as I shift my patch in the second image to the right, what's the quality of the match that I find? Or as I shift it to the left, what's the quality of the match that I find? And this quality has here been color-coded into this gray-black picture. Okay, so the important thing is the interpretation of these axes here. On the right axis, left to right, is the location of the reference patch on this blue line segment. And on the other axis, on the y-axis here, is the disparity, and color-coded is the quality of the match. And in this example, black means low cost, and white means high cost. So what we could do now, the very first thing that you would do naively is you ask for each and every offset, or for each and every location of the reference patch, you ask, what is the best, where do I find the best match? So I'm looking for the blackest spot on this in this column here, and the blackest spot in this column, I don't know, it's maybe here. The problem is that there is a fairly big black patch. Can you describe to me, when does this happen? When do I get such big black patches? All right, so you rightly said that we mainly have problems when the reference patch has little discernible texture, because then we might find many wrong matches that I try to show here, that are matches in the wrong places, but we don't notice because they're not sufficiently different in appearance. And I just mentioned that, so if we just decide here column by column of where do we put our minimum, then we will get an estimate from each and every column, but these estimates can be very noisy, and then if I plot from left to right the index at which so the disparity index at which the best match was found, I get a very rugged line, and this rugged line, of course, this is my depth estimate on that line. Now that can be super noisy. To make it less noisy, one way forward is to use bigger comparison patches, and that works. It does make the estimate less noisy, but at that point you also start losing thin structures, which is also not good. So it is important to try and get an estimate which is less noisy. So what do we want to do? On the one hand, we want to find here in each column the blackest possible spot, but on the other hand, we want to penalize depth transitions. Now, to penalize depth transitions, we can invent many different penalty functions. For example, we could say that the penalty function that I invent is just a parabola. So the bigger the disparity difference between one column and the next, the bigger my penalty. The problem is, if I use a parabola, it will over-smooth. So other choices are that people say, all right, let's use a parabola for small disparity differences, and for larger differences, we just demand a fixed fee. So the idea is that you try and smooth things, but sometimes we do have jumps in depth, where we have occlusion, like here. So the cone is in front of the face, there is occlusion, there is a depth jump in the real depth map. Then we do admit that jump, and we only charge for it once, no matter how far the jump in depth is. All right, and so what we do is we set up a problem like so. So in the language, or in the kind of diagram that we looked at in the Prince computer vision book, we would have here for this column, we would have here these various states, and I cannot draw them all because I probably have something like 40 or 50 possible disparities, so I would need 40 or 50 nodes here. And then for, so this was this column here, and then for the immediately adjacent column, I get that same number of nodes again. I just draw them at a bigger distance here. And now we have these gray values along those columns to tell us how good a match is that. In the notation that Prince used, I would put these costs next to my states. Whatever, there was a cost of 7.3 here, making up these numbers, and there was only a cost of 2.8 there, and whatever. On you go. So we have these costs associated with all the states. And now we have the costs associated with edges. And in principle, we want to admit all transitions, because we can have big jumps in depth. So if I have 50 states, then I have 50 arrows here. And I have 50 more arrows there, so it's plenty of arrows. And the weight for these arrows, well, that comes from whatever weight function I have decided to use. So, for example, this is starting to become messy. Let's say here, it means I have no depth transition at all, and I use a cost of 0. Let's say there, this is a depth transition of 1. Perhaps I'm using a penalty of 1. Then the next one has a depth transition of 2. And I'm just using the simplest possible parabola here. So let's say 2 to the square is 4. And now the point very far away, let's say we truncate it here so if this is 1, 2, 3, and we had values here of 2, 4, and 9, let's say we truncate at 9, then the cost down here would just be a 9. Right? And now we do it, of course, similarly for each pixel. We have a cost of 0, we have a cost of 9, and another cost of 9, another cost of 9, excuse me, there of 9, and so on. So we built this huge, pretty big trellis graph for each scan line, and then we look for the shortest path from S, which connects to all of these, to T. And subject to these smoothness constraints, we here find some shortest path, yeah? So it always goes through these black regions, and it should be relatively smooth, but excuse me, sometimes we said there are jumps in depth. So I do have these discontinuities at a few places where an object was in front or in back, etc. Okay. All right. And this thing now translates to one line of my depth map. Good. And now we can do that for each line in the image, and we get something which will at least be somewhat smooth in the XY direction, or in the X direction. We still see a lot of noise in the Y direction. So then one can say, all right, why not do the same thing that we've just done with the smoothness priors? Why not repeat it in the Y direction, etc. And if you do that, you get a method called semi-global matching, which is a really important method to estimate stereo images. All right, so I hope you see the connection to what we've worked through before, except that this time, to really model it, we didn't have just 5 states, but we had very many for all these possible disparities. And you see that to keep things simple, of course, Prince used few arrows here. So this state connects only to this one and to that one, and not to all others. And here, for our stereo example, we have these dense connections. So a lot of connections, but on the other hand, it's a very uniform trellis. It's all very parallelization friendly and GPU friendly, so you can compute this in no time at all. Okay, just another word on modeling. If you don't like paying costs for the nodes themselves, then you can also split the nodes. Yeah? So, for example, if Print says that we have associated with this node here a cost of 2.3, but if you don't like costs in nodes, well, then you can just repeat this node and say, all right, we now give this edge here a cost of 2.3. So we would put a cost of 2.3 here to say that is the unary cost if we go through that node, and well, the other edges are as we discussed before. I'm just mentioning it because sometimes if you're using ready-made code, you may have unary terms, but the ready-made code may not allow having costs for the nodes, and so you can mess with your graph to still represent those unary costs. Also, if you don't like having this kind of a graph structure where we have these alternations of, all right, these are unary terms, and then come again pairwise terms. If you don't like this alternation, then you can always absorb the unary terms in the pairwise terms. So, for example, here, if I had some weight, I could always, delete these extra node and these extra edges, and then just say, all right, I add 2.3 to all outgoing edges, and then I have the same thing. And that's of course what you would do in real life rather than, I mean, it will make your graph smaller and simpler. So that's what I mean is by saying that you can always absorb unary in a pairwise term. So if I have some pairwise term depending on states A and B, or states at, let's say, 2 times A and B, plus a unary, you can always say, all right, I have some psi tilde where this unary term has been absorbed. Good. I mentioned earlier the graphical models and such. These are an important class of models at the interface of stochastic modeling and optimization. And in such models, well, they're useful to reason about problems and to reason about inference in problems. And the kind of problem that we had up there was essentially of the form, if I absorb the unaries in the pairwise terms, then the problem above is really this one here. Well, we have a sum over many pairwise potentials, and then here Z would be the state. So in this kind of picture here, we have from left to right an index, for example, over time, and then we have here the different states. So, for example, this here altogether would be my state Z1, which is a vector. It's an indicator vector of 0 or 1s. This here is Z2, and so on. And well, I can express these constraints. I can say that, for example, I could say that here each element K well, I can directly say it shall be 0 or 1, and I can say that summing over all these different states here should be 1. So I want a one-hot encoding out. I want exactly one of the states in the end to be 1 and the others to be 0. So this is one way of how I can encode a solution such as this one here. But the beautiful thing is that shortest path will give us a solution that fulfills these properties here automatically. Then we have these potentials that encode the cost for different combinations here. And so the kind of model, which you see on the right-hand side, if I write it as an equation, it looks like this. I have an energy which depends on all of these indicator vectors, and it is just a sum of pairwise terms. So we have here psi I, so it depends on the states at times I and I plus 1, and then on these vectors describing the solution or state at time I and at time I plus 1. All right. Now there is something which I want to introduce briefly called a vector graph, namely, so I can summarize the kind of diagram on the right-hand side as follows. I can say that these are my different states, Z1, Z2, and so on. And now whenever I have a summand in my energy function, which involves two of these variables, or these vectors of variables, then I will introduce a special symbol connecting the respective random variables or variables. And the symbol traditionally in vector graphs is a box. So I have one term in my energy that depends on state 1 and 2. I have one term that depends on 2 and 3, and so on. But I do not have a term, for example, that depends on 1 and 3. If I did, I would have to include it here. But we've seen that I only ever had contributions here between, let's say, one time step and the subsequent time step. All right, and I'm mentioning it here because later in the lecture we will talk about message passing on trees, not just, you see this thing here, it's a chain, right? It's a one-dimensional string of variables. But actually using dynamic programming, we can do global optimization also on trees of such structures. And we will revisit this problem of solving dynamic programming problems on trees. And then I will come back to the picture that I have just drawn here. Good. Yeah, I think it will probably be useful if you ask a few questions at this point.